Nobody planned for what happened next. That is the part of this story that the people involved are still processing, years after the decision was made, and the work began, and the shells went into the water, and the results started coming back in ways that exceeded every projection that had been put on paper before anyone dropped the first load. Scientists who study marine ecosystems professionally, people who have spent careers developing precise and appropriately cautious expectations about how restoration work proceeds and at what pace and with what limitations, found themselves looking at data that did not match their models, not because their models were poorly constructed, because what formed out there in the Gulf of Mexico moved faster and grew larger and functioned more completely than anything the models had been built to anticipate. To understand why, you have to start somewhere that seems completely unrelated to oyster shells and offshore reefs and the warm, shallow waters of the Gulf. You have to start with what Florida's coastline actually was before it became what most people alive today have ever seen. The Gulf Coast of Florida is one of the most ecologically altered shorelines in the Western Hemisphere. That statement does not register properly the first time you hear it because the coastline still looks like a coastline. There is still water. There are still birds. There are still fish visible from bridges and piers and the edges of mangrove forests that line portions of the shore. It does not look like a place that has been fundamentally transformed because the transformation happened gradually enough that each generation inherited the altered version as the baseline and had no experiential reference for what preceded it. What preceded it was a reef system of extraordinary scale and density. Oyster reefs, specifically, running along the Gulf Coast in formations that in some areas extended for miles, and in others created elevated structures that were navigational hazards for small boats, meaning they were large enough and solid enough that mariners had to account for them. These were not thin scattered beds of shellfish in the way the word bed might suggest to someone who has not seen an intact oyster reef. They were architecturally significant structures built over centuries by successive generations of oysters cementing themselves to the shells of previous generations, creating limestone-like formations of extraordinary hardness and complexity. Oysters do not simply sit in the water and filter it. They build. Every oyster that settles on a hard substrate and grows and eventually dies leaves its shell behind as a foundation for the next generation. Over time, that accumulation produces vertical structure that rises from the seafloor and creates habitat of a complexity and density that flat, sandy, or muddy seafloor simply cannot support. Hundreds of species use oyster reefs as nursery habitat. Juvenile fish of enormous economic importance, including red drum, spotted sea trout, and sheep's head, depend on the crevices and surfaces of reef structure for shelter during the most vulnerable period of their development. Remove the reef, and you do not simply remove the oysters. You remove the physical architecture that an entire community of species was organized around. By the mid-20th century, Florida had lost the overwhelming majority of its historic oyster reef habitat. The causes were not mysterious, and they were not the result of a single decision or a single industry. They accumulated the way ecological losses almost always accumulate, through a combination of overharvesting that took not just the animals but their shells, through water quality degradation that made spawning and settlement increasingly difficult, through the physical alteration of shorelines and the disruption of the water circulation patterns that oyster larvae depend on to find their way to suitable substrate, and through the simple passage of time during which the shells of dead oysters dissolved back into the sediment rather than being replaced by new reef material growing on top of them. The shell loss is the part that most people have not thought about, and that turns out to be central to understanding what eventually happened when Florida started putting shells back. When an oyster reef is harvested for its animals, the shells are the part with no immediate commercial value. They are heavy and bulky, and historically they were often left on land or dumped in places where they served no ecological function. The animals were removed and processed and eaten. The shells, which are the infrastructure, the physical foundation on which future generations of oysters would have settled and grown, were taken out of the system permanently. Decades of harvesting that removed the shell material created a deficit in available hard substrate, that the ecosystem could not repair on its own because there was nothing left for new oyster larvae to attach to. The cycle had been broken not just at the biological level, but at the physical level. This is the problem that Florida's reef restoration programs set out to address when they began scaling up efforts to return shell material to offshore waters. The logic was straightforward, even if the execution was enormously complex. If the reason oyster reefs cannot recover naturally is that there is no hard substrate for larvae to attach to, then providing hard substrate should enable recovery. Oyster shells are the ideal substrate because their surface chemistry and texture are precisely what oyster larvae have evolved to recognize and settle on. They are, in the most literal sense, the material that oyster reefs are made of. Returning them to the water is not a foreign intervention. It is a restoration of a physical condition that the system already knows how to respond to. What Florida began doing, through a combination of state agencies, university research programs, and conservation partnerships, was collecting oyster shells from restaurants and seafood processors that would otherwise send them to landfills, and depositing them in targeted offshore locations where historical reef habitat had existed, and where water quality and current patterns suggested conditions were suitable for recruitment. The collection programs grew, the partnerships multiplied. The tonnage being returned to the water increased year by year as the infrastructure for collection and transport became more efficient, and as the evidence from early restoration sites began generating the kind of data that justified expanding the program's scale. 500,000 tons is a number that is difficult to hold in your mind in a way that means anything concrete. It helps to think about it in terms of physical volume. 500,000 tons of oyster shells, which are dense and heavy objects, represents a quantity of material that, when concentrated in offshore sites, creates formations of significant elevation and lateral extent. These are not thin, scattered layers of shell. They are piles, berms, ridges of accumulated material that rise from the seafloor and create the vertical structure that defines what a functional oyster reef actually is. And what happened on those piles exceeded what anyone had projected. The timeline of colonization on the restored sites was the first thing that surprised the researchers monitoring them. Oyster larvae, which are microscopic and planktonic and drift with currents until they find suitable substrate and settle, found the shell deposits within weeks of placement in some cases. The settlement rates recorded at multiple restoration sites in Florida's coastal waters were at the high end of what would have been considered optimistic in planning documents, and in some locations they exceeded those projections significantly. The shells were doing exactly what shells are supposed to do, which was providing the substrate that larval oysters recognize and respond to, and the larval oysters were there and ready to respond, because the surrounding waters, despite their degraded condition relative to historical baselines, still contained reproducing oyster populations whose offspring had nowhere adequate to settle before the shells were placed. Within a single growing season at the most successful sites, the deposited shells were no longer simply shells. They were reefs. Living, actively growing structures with oysters of multiple size classes, representing multiple generations of settlement, the older individuals providing additional shell surface for newer settlers, the whole assemblage beginning to develop the three-dimensional complexity that distinguishes a functioning reef from a pile of substrate material. But the oysters themselves, while central to the story and remarkable in the speed and density of their recovery, are not the finding that most surprised the scientists monitoring the restoration sites. The oysters were expected. Their arrival was the goal. What was not fully anticipated, or rather what was anticipated in principle but not at the scale and speed at which it materialized, was everything that arrived because of the oysters. Within 2 years of the establishment of oyster reef structure at restored sites, fish community surveys conducted by researchers from Florida's University marine science programs began returning numbers that were difficult to contextualize against the surrounding baseline. The species richness, meaning the number of distinct fish species using the restored reef habitat, was dramatically higher at restoration sites than at comparable unrestored seafloor in the same areas. The abundance of juvenile fish, the individuals in their first year of life using the reef structure for shelter and foraging, exceeded anything the surrounding habitat was producing by margins that were not subtle. At some sites, the difference was not a modest improvement. It was a transformation of the ecological character of a section of seafloor that had previously been functionally empty from the perspective of fish habitat value. Red drum juveniles appeared in survey nets at restored sites at densities that researchers described in their documentation as striking. Spotted sea trout, a species of enormous recreational and commercial importance, whose populations in many parts of Florida's Gulf Coast had declined significantly over previous decades, used the restored reef structures for spawning in ways that were recorded and documented by acoustic monitoring equipment placed at the sites. Sheepshead, black sea bass, lane snapper, gray snapper, species representing different ecological roles and different habitat requirements, but all sharing a dependence on hard-structured substrate, arrived and established themselves in numbers that built year over year as the reef itself grew and matured and developed additional complexity. The filtering capacity of the restored reefs began producing measurable effects on water quality at and around the sites. A single adult oyster filters approximately 50 gallons of water per day, removing suspended particles including algae, bacteria, and organic material from the water column as it feeds. 50 gallons per day per animal, multiplied across the tens of millions of individual oysters establishing themselves on the larger restored reef complexes, produces a filtration effect that is detectable with standard water quality instrumentation. Clarity measurements at sites with established reef structure showed improvements that corresponded to the growth of the oyster populations and that had downstream effects on the light penetration available to seagrass beds in adjacent areas. Seagrass is the part of this story that connects the offshore reef restoration to the broader coastal ecosystem in ways that took some time to fully document and that represent perhaps the most significant finding to emerge from the Florida program. Seagrass beds are among the most productive and ecologically important habitats in coastal marine systems. They serve as nursery habitat for species including commercially important shrimp and the juvenile stages of numerous fish. They are primary feeding grounds for sea turtles and West Indian manatees, both of which are species of conservation concern in Florida waters. They absorb carbon at rates comparable to terrestrial forests, and they require clear water with adequate light penetration to survive. Florida's coastal seagrass beds had been declining for decades, in significant part because of the water clarity problems associated with nutrient pollution and algal blooms that the same degraded coastal conditions that eliminated oyster reefs had produced and sustained. The connection between oyster reef loss and seagrass loss had been understood theoretically. What the restoration program began producing was empirical evidence of the connection running in the other direction, with restored oyster filtration capacity contributing to clarity improvements that allowed seagrass to begin recolonizing areas from which it had retreated. The researchers documenting this were careful about their language, as researchers are trained to be, qualifying their findings with appropriate discussion of confounding variables and the limitations of attribution in complex ecological systems. But underneath the careful language was something that did not require qualification. They were watching an ecosystem remember itself. They were watching a system that had been disrupted and degraded over a period of more than a century begin to reassemble the relationships and the functions and the biological communities that had characterized it before the disruption, because one physical element of its architecture had been returned. And the system had responded to that return by doing what functional coastal ecosystems do. The economic analysis that accompanied the ecological findings added a dimension to the story that proved important for sustaining political and financial support for the program. Oyster reefs function as natural wave attenuation structures. Their physical presence in the water column dissipates wave energy before it reaches the shoreline, reducing the erosion that in their absence acts on coastal land at rates that are enormously expensive to manage through engineered solutions. The value of the shoreline protection provided by restored reef structures, calculated as the cost of the engineering alternatives that would be required in their absence, proved in multiple analyses to exceed the cost of the restoration work itself. The reef was not just an ecological asset. It was infrastructure, in the economic sense of the word, providing services whose value could be quantified and compared against the investment required to produce them. What Florida had done across years of accumulating program scale and accumulated shell material and accumulated evidence from monitoring programs was demonstrate something that coastal managers and marine ecologists had been arguing for years without sufficient empirical support to make the argument as forcefully as the situation required. They had demonstrated that the ecosystems of the Gulf Coast were not gone. They were suppressed. They were waiting, in the sense that the biological and physical potential for their recovery existed and remained present in the system for the conditions that would allow them to express themselves again. The oyster larvae were always there. The fish were always there. The seagrass was always there at its margins, ready to expand if the clarity returned. All of it was there, compressed and diminished but not eliminated, waiting for something to return that it could organize itself around. 500,000 tons of shells was what it took to begin demonstrating that. 500,000 tons of material that restaurants and processors had been sending to landfills, treated as waste, understood as having no value after the animal inside had been removed, turned out to be precisely the thing that the Gulf Coast had been missing for a century. The waste product of the industry that had helped destroy the reef was the material required to begin rebuilding it. There is something in that circularity that deserves more attention than it usually receives when this story is told. The shells that went into the water were not new material. They were not engineered or manufactured or designed by people who understood reef ecology and produced something optimized for larval settlement. They were the same shells that had been building those reefs for thousands of years before commercial harvesting removed them from the cycle. They were the shells that belonged there, that had always belonged there, that the system had been trying to replace and could not because they kept being taken out. Putting them back was not a technological intervention. It was a correction. It was the reversal of a specific error that had been made so incrementally and over such a long period of time that it had ceased to be visible as an error and had become simply the condition of the coast as people knew it. The reefs that have formed on the restoration sites in Florida's Gulf waters are young by the standards of the historic structures they are meant to replace. The largest and most complex oyster reefs that once characterized the Gulf Coast had been building for centuries, and the restored reefs are measured in years and decades rather than centuries. They are not yet what the original reefs were. They are not yet as tall or as extensive or as structurally complex as the formations that 18th and 19th century mariners navigated around. But they are growing. Every year they are larger and more complex and supporting more species and filtering more water and attenuating more wave energy and expanding the seagrass at their margins than they were the year before. They are doing what oyster reefs do when they are left to do it, which is build, continuously and cumulatively and without requiring anything from the humans who watch them, except the material they need and the space to grow. The people who dropped the first loads of shell into those offshore sites did not know exactly what would form. They knew the theory. They understood the ecology in the way that scientists understand it, which means precisely and partially and with a clear sense of what the data could and could not support as a claim. They knew that providing substrate should enable settlement. They did not know at what rate. They did not know how quickly the fish communities would respond, or whether the seagrass connection would prove empirically demonstrable, or whether the water quality effects would be measurable within the time frames that monitoring programs could reasonably sustain. What formed exceeded what they knew how to predict, not because the science was wrong, but because the system, given the conditions it needed, performed at the upper bound of what was possible rather than the expected middle of the range. It performed as if it had been waiting, as if the century of degradation had compressed something rather than destroyed it, and the compression released when the substrate returned. That is not language that appears in the peer-reviewed literature on oyster reef restoration. It is not the kind of claim that ecological science can formally make because the system does not have intentions, and compression is a metaphor, and waiting implies an agency that a marine ecosystem does not possess. But it is what the data looks like. It is what the researchers who spent years at those sites, pulling survey nets and reading water quality instruments, and mapping the expansion of seagrass at the reef margins, describe when they are not being careful about their language. It is what happens when you return something to a system that was organized around it for thousands of years before it was taken away. The Gulf does not forget. It cannot forget because forgetting requires a mind, and it has no mind. But the relationships are encoded in the biology of every species that depends on the reef, in the behavior of oyster larvae that respond to shell substrate with a specificity that evolution has been refining for longer than human civilization has existed, in the movement patterns of juvenile fish whose instinct to seek structured, hard substrate was shaped by millions of years of reef habitat being present and available. Put the shells back and the system responds as if it has been waiting, because in the only sense that matters ecologically it has been. The potential was always there. The biology was always there. The relationships were always ready to reassemble. What was missing was the physical foundation on which all of it could stand. 500,000 tons, and something that had been gone for a century came back.